Recording in progress. Hey guys, Mr. Riz here to help you out with the 1.2 video notes for Algebra 2. Here we go. This one we're looking at linearity, intercepts, and symmetry. Okay, so a little warm up here from the last section. What you want to do is kind of pause this video and see if you can write the domain and range of each function. All right, let's check our answers here. All right, so if we look at this function here, we got 3 goes to -3. We can see here the x's are opposites of y's, so that should be y equals -x. The domain, and you always start with domain with the smallest number here. We got -7, then we got 3, 4, and 6. And the range, same thing, we start with the lowest one, -6, -4, -3, and +7. Second one here, if we look at the equation here, if we look 0 goes to 0, 4 goes to 12, 2 goes to 6, -1. So it's y equals 3x. The dependent variable is 3 times the independent variable. The domain, we start with the smallest number here, -1, 0, 2, 4. Range, -3, 0, 6, and 12. Okay, and the next one here, if we look, 2 goes to 1, 8 goes to 4. We're cutting those in half. So the equation be y equals 1/2 x. Check the domain. Check the ranges out. Domain is x, range is y. The easy way to remember it, x comes before y, d comes before r in the alphabet. Next one here, 8 goes to 7. You can see each one, we're just going down by 1, so it should be y equals x minus 1. The domain, check the x's, check the y's. All right, not too bad. Here's the math standards. All right, here's our goal here. Hopefully by the end of this video, you can identify linear and nonlinear functions. You can identify and interpret the intercepts of functions. Ooh, and hopefully we're still good. We can identify whether graphs or functions possess a line or a point of symmetry and determine whether the functions are even, odd, or neither. Okay, so linear functions here. A linear function basically has no variable is raised to a power more than 1. Okay, so any linear function can be written in the form of, f of x equals mx plus b, where m and b are real numbers. Okay, they can be fractions, they can be decimals, they can be whole numbers, positive or negative. Linear functions can be written as linear equations, which can also be written in the form of ax plus by equals c. So this one here, you guys might have known as y equals mx plus b, that's slope-intercept point. It's the best for graphs. This one is standard formula for linear equations. This one's actually really good for finding x and y intercepts. Both are good for their own reasons. We'll go through. All right. The biggest thing is the graph of a linear equation is a straight line. That straight line can be diagonal either way, or it could be horizontal. Okay, a function is not linear, or also known as a nonlinear function. Okay, if the graph of the function includes a set of points that can not all lie on the same line. All right, so if it's curved at all, then this is a nonlinear function. A nonlinear function can be written in the form, cannot be written in the form of fx equals mx plus b. So a parabola is a pretty classic example of a nonlinear function. Okay, what you're going to do is look at these ones here and try to guess if it is linear or not. We got f of x equals 6x minus 5 all over 3. And then the other equation here, we got 5y equals 4 plus 3x. Go ahead, pause the video, give this a try. All right, so with this first equation here, if you're going to try to get the y by itself or the fx by itself, okay, what you would do is distribute the denominator here. So we divide both of those by 3. We get 6/5x minus 5/3. 6 divided by 3 is 2x, and 5/3 is just 5/3. It doesn't simplify at all. So this function can be written in the form of mx plus b, where m is 2 and b is -5/3. So it is a linear function. All right, now with this other equation here, if we were going to try to get the y by itself here, we would, let's see, well, the 5y by itself, it's good. We'd probably want to move the x over first, and we'd have a 3x cubed. Now, this function cannot be written in the form of the fx equals mx plus b, because the independent variable, the x, is raised to a number greater than 1. Okay, it's cubed. If it's cubed squared to the 99th power, it's not a linear function. So this is a nonlinear function. Okay, next what we're going to do is look at graphs to see if they are a linear function. So go ahead, pause, see if you can figure these ones out, and let's check our answer. Okay, this first one, there is, even though that we have straight lines here, there's no curves, there is a bend to the graph. So this is a nonlinear function. Points A, B, and C do not all line up on the exact same line. A and B are on the same line, B and C are on the same line, but not all three of them are on the exact straight line. All right, next one here, we got these 3 points. They all lie on the same line. So this is a linear function. I would say this is pretty easy, right? Straight line, it's a linear function. All right, now we got a question here for you. Think about it. If we have the equation, the square root of 2x plus 3, is it a linear function? Pause, think about what your answer would be. All right, so this one is not a linear function, okay? So one thing we will learn later on in Algebra 2 is that the square root technically is an exponent to the 1/2 power. So that is not to the first power. And that is, even though it's not greater than 1, it still does not work. If you were to graph this equation, you could see it actually makes a nice little curve. So it's a curved line, not a straight line. All right, now, same thing that we're dealing with. Let's look at these in story problems. So here we got an equation or a story. Michaela is starting to work a part-time job at a local hardware store. Her time at her work steadily increases for the first 5 weeks. The table shows her total earnings each of those weeks. Are her weekly earnings modeled by a linear or nonlinear function? All right, so you can see week 1, she got 85, then 2, 119, 185. So take a second, think about this one here. Let's go over it. Okay, if we were to graph those points, we can see here we got a very nice straight line. Since there is a line that connects all the points, this is a linear function. The other thing we probably want to do, and can go back, is to double check that we are increasing by the same rate each time. So the one thing with graphs, especially story problems, if they vary differently, it's technically not a linear function. So we got 85 to 118. That's what? Is that 34? Yeah, no. Yeah, 20. Yeah. And then we go up again, another 34, another 34. Okay, so we are increasing the same amount each time. That is a linear function. Okay, hopefully we got an idea of what's linear and nonlinear. Next, let's talk about intercepts. So a point at which a graph of the function intersects an axis is called an intercept. An x-intercept is the x-coordinate where the point crosses the x-axis. The y-intercept is the y-coordinate where the point crosses the y-axis. Makes sense. All right, a linear function has at most one x-intercept, while a nonlinear function might have more than one, okay? No function will have more than one y-intercept. All right, so we're going to use the graph to estimate the x and y intercepts here. So pause, take a second, remember what those definitions are. Let's see our work. All right, so the graph intersects the x-axis, this left and right line, right here at 0, 0, 0. So the x-intercept is 0. It intersects the y-axis right here in the middle again at 0, 0. So the y-intercept is 0. So we could potentially have a graph like this one here that has the same x and y intercept. All right. So can we describe a line that does not have 2 distinct x-intercepts? Okay. We could have multiple ones here. So, all right, actually, this one, not a line here, but we could have something where we have a vertical line or horizontal line where we have a single intercept, but we don't have a y-intercept. We could, no, this shouldn't be a curved line at all. That is not a line. Okay. But potentially we could have later on where we could have nonlinear functions that only cross the y-axis and not the x. And then something like we just looked at, a diagonal. Those are not 2 distinct functions. All right, now let's look at nonlinears and see if we can still figure out those x and y intercepts from the graph. So pause this video, see if you guys can estimate the x and y intercepts. All right, let's start with the x-axis. It looks like the x intercepts at -3, 0, -1, 0, and it also touches right here at 2, 0. So this function has three x-intercepts of -3, -1, and 2. Those are also going to be called roots. We'll learn about that later on in this year. Where does it cross the y-axis? It only crosses the y-axis right here at, now be careful with these, we got 4, 8, right there at 12. So 0, 12, so it had the y-intercept of 12. I find it easier to look at these numbers and then name them as points. So remember when you're finding the x-intercept, you got the numbers there, you put the x number first and then a 0. If you're looking at the y's go second, and you put a 0 in front of it. Okay, next, let's think about this. Could we have a graph of a nonlinear function? The graph of a nonlinear function has three x-intercepts. Can the graph have more than one intercept? Let's try to explain the reasoning here. Okay, no. If there's more than one y-intercept, it would not pass the vertical line test. So let me try to draw this out real quick. So we have a graph here. All right, and color. So say we have a graph and it's going to cross the y-intercept at more than one point. What's got to happen? It's got to go up and then somehow curve back. And if we look here, the vertical line test, if you remember from Algebra 1, if you ever have more than one, a domain, an x value that has more than one range, it is not a function. So you can see here, like at 1, you'd actually get 1, 2, 3 different numbers for the value of 1. So that's technically not a function. Okay, let's kind of test our skills here. Let's see if you guys can look at these graphs and determine the x and y intercepts of each one. So pause the video. Let's write these down. Okay, let's check out our work here. All right, the x-intercept here is at -5. The y-intercept is at +2. There's just one x and one y. It crosses the x at one spot, two spot. Now this one crosses the x at 1, 2, 3, 4, 5 different spots. So we have 5 different x-intercepts at -4, -2, at 0, at 3, and at 5. Where does it cross the up and down line at? Just right here, smack dab in the middle at 0. Okay, kind of doing the same thing here. We have a story problem here. So finding the x and y intercepts based off of a story. So Ricardo launches a rocket from the balcony. The table shows the height of the rocket after each second of its flight. We're going to try to identify the x and y intercepts of the function of the model. And then what's the meaning of these x-intercepts? Okay, so we look here, 0, 15, keep going through. All righty. Let's take a second, think about these, answer those questions. Let's pause the video. Let's check our work. So if we're looking at that graph here, the x-coordinate is when y equals 0. So that is right at 8. So the x-intercept is at 8 or 8, 0. All right. The y-coordinate is when x equals 0. So when does x equal 0? That's at 15. So that is the y-intercept is at 15. So go back to the table there. All right, the x-intercept is when the x equals 0. Or no, when the y equals 0. So right here is the x-intercept. This is the y-intercept. Okay, what does that mean? So the x-intercept is the number of seconds after the rocket is launched and returns to the ground. Okay, the y-intercept is the height of the balcony at the beginning. So we can determine that information just based off of the story and the graph or the table. All right, ready for the third and last section of this. We're going to be looking here at symmetry. So a figure has symmetry if exists a rigid motion, either reflection, translation, rotation, or glide reflection that maps the figure onto itself. Okay, so a couple different types of symmetry here. We can say a graph has line symmetry if it can be reflected in like a vertical line so that each half maps exactly right on top of each other. Okay, we look here, we have vertical line symmetry because if I flip this point over there, it's the same. Same thing, if I flip point A over here, it's the same. So the line dividing the graph into matching halves is called the line of symmetry. All right. Each point on the line is reflected to the other point and it's equal distance from the opposite side. Okay. We could have point symmetry. So here we would have a point symmetry right here at 0, 0. And when it's rotated 180 degrees, either clockwise or counterclockwise, it reflects onto itself. So if we look at a point here, we were to rotate this point 180 degrees around point 0, we'd have that point there. So that point is called the point of symmetry. Okay. So it's still going to be equal distant from that point. If we to do the distance form from here to here, it'd be the same from here to here. Okay. Now, what kind of helps us with symmetry are knowing whether a function is even or odd. So a function is that has line symmetry with respect to the y-axis is called even functions. Okay. So if we have a y-axis that splits the function right in the middle, this is called an even function. Now, mathematically, we can test this out without looking at a graph, is if we do f of negative x, meaning we replace all of our x's with a negative x in parentheses, if we essentially get the exact same function. All right. A function is considered an odd function if it has a symmetric point, a point of symmetry to the origin. So we can rotate it around. So mathematically, we can determine that by going through f of negative x again, but this time we get a negative, a complete opposite version of the original function. So we'll do a couple of examples of that. So we're going to test each graph here and try to explain what we got going on. All right, so we got f of x equals 3x minus 1, and then we got g of x equals negative x squared minus 4x minus 2. So think about that. Maybe looking at the graphs, could you determine, are these even or odd? What type of symmetry do we have? So, like you can see here, we definitely have a vertical line of symmetry here, but does that mean it's even or odd? Can we flip that over or rotate this one? Maybe. Let's see what it looks like. All right, so this one does have a point of symmetry. If we were to take a point on this graph here, we're just looking at types of symmetry, not even or odd. We could rotate this one here around itself 180 degrees. It would be the same. Now, this other one does have line symmetry here. The line is not the y-axis, but it is right over here at -2. It would be flipped over itself. Those things are always good to know. All right, next one. Let's look at these here, determine if these have any type of symmetry. Pause the video, give it a shot. All right, so in this problem here, this first one, there's no symmetry. There's not a single point that we could turn and rotate. There's not a line that we could make to flip them over each other. It's kind of wonky shape there on the left and right side. It's not even. Now, D here does have point symmetry. We could put a point right there in that reflection point there, and we could rotate that around. So there's a point right there at 0, -2. Okay. How would you know the type of symmetry help you graph a function? Think about this here. Pause the video. See if you can think of a reason why it's important when we're graphing functions to know the type of symmetry. Okay. So you might have to think outside the box here. What if we were trying to graph without using Desmos? If we know that we can find the point of symmetry or the line of symmetry here, what we can do is use that as our values, and everything on the opposite side would be the same number. Okay, so we can go through and basically eliminate half of our work if we know where to reflect it or rotate it. Okay, next, let's look at this kind of algebraically, see if we can determine whether these are even or odd. Remember, even functions can be reflected over the y-axis. Odd functions can be rotated around the origin. Okay, so we could have even, odd, or neither. All right, now this first equation here, if we're going to go through this, what we want to do is to take this f of x and change all the x's to negative x's in parentheses. Okay, then we're going to go through and simplify. Okay, so if I were to take negative x and cube it, a negative times a negative times a negative is still a negative. And then if I have -4 times negative x, the minus in the 4 actually just turns that into a plus 4x. Now, if we want to turn this back into a positive x cubed, I have a negative x cubed. I could factor out a -1, and that would make this a negative times positive x cubed, and then the plus 4x, if I factor out a negative 1, becomes a minus 4x. And so if we look at this, really this is negative times x cubed minus 4x, which is our original function. So because we have f of negative x turns out just to be the complete opposite of the original function, this is an odd function, and it is symmetric around the origin, a point of symmetry. I'll pause the video for a second here. That did not pause. I just show my screen. Let me make sure I'm still sharing my screen. We're good. All right, sorry for my coughing. All right, next, let's look at this one here. You might think here it might be vertical line. It might be even because of that. Let's double check. All right, so if we were to go through and plug in a negative x into both of those spots. All right, and then we're going to simplify this here. A negative times a negative times a negative times a negative, okay, basically becomes a positive. So this negative x to the fourth power just stays positive, x to the fourth power. And the negative 6 times negative x squared, negative times a negative is a positive, that stays a positive. So if we look at that, that is the exact same equation we started with. It did not change, even though we made it a negative x. So since when we plugged in the negative x, it remains the same, this function is even, and it's symmetric across the y-axis. All right, so we see what an odd function is, and now we see what an even function is. Let's see, is this one even or odd? Could we rotate this one here? All right, so if I take negative x cubed plus 0.25 negative x squared minus 3 negative x. Okay, what we want to do is to simplify this. Negative times a negative times a negative makes that a negative x cubed. The negative x squared is a positive 0.25 x squared. And then we have here a negative 3 times x, all right, is a positive 3x. Now, if we try to turn that into a positive, we could factor out a negative, but then that becomes a positive, then a negative in the middle, and a negative at the end. It is not the exact same that we had. It is not the original or the complete opposite. It's just something different. So that one is neither even nor odd. Okay, so let's think about this here. What if I just gave you a point here? So this is the kind of the last thing we're going to think about here. What if I said there's a function that has a point at 2, -5? All right. What if I told you that this function is even? Could you tell me another point? Think about it, pause the video. Let's try to do this together. All right. So if this is an even function, remember our f and negative x, or x and negative x would have the same value. So we would have another point at -2, -5. So basically change that. Now, if we were going to go through and have an odd, we could rotate it and basically switch the signs on both of those. So there'd be another point at -2, +5. They'd be complete opposite. Okay, so you can see here, the evens are directly across from each other, left and right. The odds are diagonal from each other, where we flip both of the signs. All right. Here we go. We got some exit tickets for us, but for you guys, remember the exit tickets are going to be the CYUs that are on there. So you guys can go over these if you'd like. Check your answers here or check your work online with the Canvas. But thank you guys for watching. You guys have a great rest of your day. I will see you guys again. And yeah, be kind to each other.